Hi, welcome back. In this lecture, we will be talking about minerals. So this begins our dive into geology, and geology really starts with minerals because they are sort of the smallest fundamental building blocks of the geosphere. Now we could start with individual atoms, but we've already talked about the composition of our planet. It's mostly iron. Oxygen, I believe, if memory serves me correct, is the next most common element. And then we also talked about Earth's surface, because that's where we live. That's how we experience the geosphere. That's made mostly of oxygen, almost 50%, and then silicon is about 25%. And then there's aluminum and iron and things like that. But it's really just the minerals that make up the rocks, the soil, the geosphere, really, in total. So today we're going to discuss what minerals are and then the different groups of minerals. So, not every compound that exists is a mineral. For the most part, all of the compounds in the geosphere are minerals. So like water, for example, doesn't count as a mineral, but it's also not really part of the geosphere. So, in order for something to be a mineral, it has to generally be all of these things. It has to occur naturally. So geologic processes form minerals. They're not synthetic. They're not man-made. Minerals are always solid at normal temperatures, which would be like, temperatures below about 300 degrees Celsius, which is very, very hot. But they remain solid up until that point. And minerals, almost all minerals form crystals. They have an orderly crystalline pattern, so they'll form cubes or diamond-type shapes, tetrahedrons, prisms, those sorts of things. Minerals are substances. So because they are compounds and substances, they are rigidly defined, meaning we can just take the elements they're made of, and it comes in a simple whole number ratio. So for example, water is not a mineral, but we'll just use that. Water is H2O. No matter how large or small of a sample of water you have, you can boil it down to just what we have here is 2 parts hydrogen, 1 part oxygen. And minerals are the same way. And for the most part, the vast majority, at least, of minerals are inorganic. So they form from the crystallization out of lava, for example. They don't form inside of plants or whatever. I mean, there are kind of exceptions to this. There's a mineral within your skeleton and in the shells of animals. Sugar is kind of like a mineral. It fits all of the categories except for it has a fairly low melting point, and it's made organically. And there are a few other things as well, which we won't worry about. So, these are minerals. This is amethyst. They occur naturally. You can see here the crystalline structure of it. They're part of the geosphere, so these are some enormous gypsum crystals in a cave in Nica, Mexico that some people are exploring. Here we can really clearly see the chemical compositions. So, like, there's sodium chloride, calcium chloride, potassium chloride, magnesium chloride, and iron chloride at the top. One's on the bottom. I guess I'm not so sure what they are. But they have a specific chemical formula to all of them. And you can see the really high melting point that they have as well. Here we can see a little more clearly that orderly crystalline structure. That looks like it's artificial, but it's not. That's really how it exists in nature. Most minerals, however, are too small to see. Here we can see some awesome fool's gold pyrite cubes. And again, a person didn't machine that to look like that. That's just how it actually looks because it's one of the definitions of them. They form crystals. Now in this case, they're large enough to see. In this case, these pyrite dodecahedrons are like 1/10 of a millimeter across or smaller, but they still form regular shapes. Here's some bismuth, which does the same kind of thing. Now, bismuth is actually an element, but it will form these orderly crystalline patterns to it as well. Here we can see some salt, like at the Dead Sea. another example, just a bunch of minerals to look at. Okay, moving on. Minerals can form in a lot of, or under, I should say, a lot of different conditions. Some form just on the surface, like we can see here, but others require extremely hot temperatures or the weight of billions of tons of rock to force the atoms to recrystallize into a new form. We can think of like maybe the way diamonds form under intense heat and pressure. So, 4 basic ways in which we get minerals. Crystallization from magma is probably the most common. So, the magma, it has the raw ingredients in it, and when it cools and solidifies, the atoms will find each other and they will form those definite chemical compounds, which end up being minerals. So they crystallize. And then we get the awesome patterns and everything from that too. There are precipitation reactions as well. So the surface water or water just below our feet, it has dissolved minerals in it. And when the water evaporates, the minerals, again, they find each other, they chemically bond, and then they form minerals. Next is really intense pressure and temperature. So one or more minerals can be forced to recrystallize into brand new forms if they are subjected to intense heat and pressure. And then finally, there is hydrothermal solution. So this is where either it's similar to a precipitation a little bit, but we need way more, the water temperature needs to be much more extreme, very, very hot. Or other times, the water actually carries with it minerals, and the water will deposit those minerals into solid rock, forming, like, this is what ore is. So like iron ore, the water introduces the iron, and then the iron atoms will chemically bond with other things like oxygen to form iron oxide minerals in the solid rock. So this is what's called a geode, and you've maybe bought a geode and cracked it in half before, but this crystallized from magma. So we can see the outer surface, it's extremely smooth and polished, and it looks uniform. There are crystals there. It's just that they're so microscopic because that part cooled down right away that we can't see the mineral crystals. They were not able to grow. But on the inside, where the geode stays hot for longer, the mineral crystals grew, and so we can visibly see the crystal structure to them. These are garnets. So garnets are a semi-precious gemstone, and they're semi-precious because they're extremely durable and they're not very common. Garnets can only form under really extreme heat and pressure conditions deep within the earth, and they actually form from other minerals that come together, and their raw ingredients rearrange themselves into the garnet. These are just salt cubes, so again, they look like they were made. They were man-made because they're so like perfect and orderly. But no, you can just find them on the shores of places like the Dead Sea or maybe Great Salt Lake in Utah. And this is an example of a precipitation reaction. The salt is in the water. When the water evaporates, this gets left behind. And this is, again, another example of heat and pressure. So serpentine, the mineral on the top left there, if there's a lot of heat and pressure, that can react with carbon dioxide to form these 3 brand new minerals. 2 brand new minerals, and then some water is left behind. So this is like a metamorphic transformation. It's a good example of heat and pressure causing change. And then this is some kind of ore, maybe it's like silver or something, but that was deposited by hydrothermal solution. And then it looks like pure metal, but in reality, the metal reacts with already present minerals within the rock to form new metallic minerals. Another example of hydrothermal solution, this cave in Nica, Mexico, originally the whole thing was underwater. So the gypsum crystals can only form if they're underwater. All the raw ingredients come together in the presence of water, but the temperature has to be right. The temperatures in this cave are really, really hot because it's very deep underground. And so that's what allowed these huge crystals to grow. So because there are only so many elements that are common, Minerals can be lumped into actually just only a few groups, and it's based on the most common elements that are within them. So the first group is the silicates. So these will contain the elements silicon and oxygen. If you see those two elements in its chemical formula, it is a silicate no matter what. And it can have other elements in there, but if you see these two, it's a silicate. And these are by far the most abundant minerals on our planet. Again, almost half the surface is oxygen, and almost 25% of it is silicon. For the most part, silicates are formed by either crystallization from magma. I don't have that on here, but either crystallization from magma or heat and pressure, so they're very hard and durable minerals. Quartz is a pretty well-known example, most common mineral on our planet. I don't know the names of all of these. I know feldspar and mica are up there, but these are just other examples. And here are some variations of quartz. Different impurities within the mineral can give it these different colors, but those impurities, we don't add them to the chemical formula because, like, we don't say salt water is H2O NaCl. NaCl is the formula for salt. No, because first of all, they're not literally chemically combined. The impurities in the quartz are just mixed with it. And it's the same with salt and water, but also there are trillions, perhaps, of water molecules for every salt compound, so it doesn't count as part of the formula. And it's the same thing with impurities in minerals. So here's just a list of a bunch of different silicates, and I picked ones with really complicated formulas with extra elements in there. But all you have to look for, like I said before, is are there silicon and oxygen atoms present? If yes, then it is a silicate. That is the rule. Next group are the carbonates. So you will have the element carbon, C, oxygen, O, and then any other metallic elements. No nonmetals, and definitely no silicon, which is a nonmetal. And this is the second most abundant mineral group. Nothing else to add to that, really. Sadly, I don't actually remember off the top of my head which carbonate mineral this is, but this is an example of one of them. And here's another. And again, sadly, I'm forgetting the name from when I made this presentation a long time ago. And there's yet another, which the name of it escapes me right now. The next group of minerals are oxides. So these will be oxygen plus some metallic element. Now, carbon is a non-metal, so that's what makes a carbonate very different. Oxides will just be the element oxygen plus metals, nothing else. And again, they can't contain silicon, which isn't a metal in the first place, but that would make them silicates instead. So here's some random oxide mineral. This one's corundum. I do remember that one. Corundum is the second hardest material on the planet. So the only thing harder than corundum is diamond. And I don't remember what this one is. Okay, sulfates and sulfides. These will contain the element sulfur, but there is a difference between them. Sulfates are typically formed by precipitation reactions, but also they must contain SO4. That's what a sulfate is. It's sulfur and 4 oxygen atoms, but then there can be other elements added to it, just as long as they're not, as long as silicon isn't one of them. And then sulfides are typically formed under more extreme conditions, and they don't contain any oxygen in them. So this is galena. Galena is lead and sulfur. So that's it. No oxygen, obviously. This, I think, is rhodochrosite, and I don't remember the formula for it off the top of my head, but I believe this one does contain oxygen. So here again we have pyrite, otherwise known as fool's gold. That is iron and sulfur combined together. And this one's very pretty, but I do not remember the name. Sorry. Then there are the halides. So these are called that because they contain what's called a halogen ion plus some other element. And the halogens are the elements in group 7A. So this would include fluorine and chlorine, the elements fluorine and chlorine. So 7A is the one labeled 17 on here. F is fluorine, Cl is chlorine, Br is bromine. So some common examples would be like this is either gypsum salt or rock salt. This is pure halite, sodium chloride, otherwise known as table salt, but it will form these large cubes if it can grow that large. And then this is fluorite. The final one, which is very different, these are the native elements. So these are different because they're not compounds actually, they're just pure elements. So this includes gold, silver, copper, sulfur, and carbon. So this is really bizarre, but this is pure or relatively pure gold. But you can see it's formed what's called a tetrahedron, which is like an 8-sided dice, a pyramid on top and a pyramid on bottom. Not very typical to see that. Here's some gold that's also formed some like really stringy, long crystals. This is kind of like what ice sometimes looks like under the microscope. It can do that under the right conditions. It's just not very common. But we're all familiar with diamond. So here's a raw diamond that has not been cut or polished at all. And again, it forms a tetrahedron as well. So that does it for introducing minerals. Next time we're going to talk about how to classify minerals even further through the special properties that minerals have.